thank you all so much for joining us today. So today we have Alberto Abadie joining us from MIT. I don't think we really need to introduce him because I think everyone knows him. He's done so much amazing work in causal inference, and I'm absolutely thrilled for this talk. I have lots of love for his work. My favorite paper is the design-based, sampling-based comparison. And I don't even know how many people I've sent that paper to, because I do a lot of design-based things, and I think that paper just provides a lot of clarity. So thank you for writing it, and thank you for agreeing to be here to lead the seminar. So take it away.
Well, thank you for it. This was such a generous introduction, and you know, this is kind of a follow-up to those papers. So like, yeah, that's good. And you know, before I go into it, I have to say that I'm very happy to be here. I spent about 17 years at Harvard with you know, a lot of people interested in causal inference in different places in the university. But you know, like we don't have anything like the causal inference seminar, and I'm so happy I could cry, but I won't. Let's talk about you know, clustering and error. So like when I you know, speak to economists about clustering, they immediately understand what I'm going to talk about. When I talk to people in machine learning or statistics about clustering, they immediately think I'm going to talk about something else. like a clustering in the sense of k-means or something like that. You will see in a moment. Okay, and of course this is joint work with Susan Athey, Guido Imbens, and Jeff Woolrich. Okay, so I'm going to do something that is relatively, you know, like unheard of in econometrics or, you know, like a presentation that is to start with an empirical data. Okay, but I think it is going to provide a motivation. So here we have, you know, like what do we have here? Let me take this point out of there. That is in the middle. Yeah. We have you know, two panels with a regression. The dependent variable is log earnings. This is data from the US Census, okay? And the treatment is going to change between the two panels. In panel A, the treatment is like defined at the level of the state. So it's like it's a state indicator for like you know, like workers having you know, like a college, like the proportion of a worker having college is more than, you know, 0.55, and we choose 0.55, so you know, these two things are nicely balanced, like you know, treated states and untreated states. In panel B, by the way, I should switch this one right there. In panel B, you know, the treatment is at the individual level, so it's an individual indicator of some college. Okay, so here we run OLS, here we run OLS, and here we run also fixed effects. That means that, you know, like we can put like an individual dummy for each state. We cannot do that in the first regression, of course, because we have a collinearity. Okay, so we obtain the coefficients. That is what the people may care about, but people care about the coefficients and care about the, you know, the precision with which you are measuring these parameters. And you know, like in economics and in the other social sciences, it is you know, like it is usual to measure this uncertainty in two different ways. Perhaps you can, you know, like use what people call like a homotheistic robust standard, sorry, heterotheistic robust standard errors that you know, think all these observations are independent, or you can, you know, like cluster your standard errors. I guess in biostatistics that will be Lian's figure, right? So that's what we have there. And it is usually like you see there like all these papers in economics in which you have this regression, you have big clusters like states or school districts, and you know, like people are, you know, like clustering the standard errors, perhaps at the level of the states, because perhaps they think that there is some, you know, like a shock that is correlated at this level. Okay, and you know, in the second regression, like we use fixed effects, as I said. Okay, so like the interesting thing here is that you know, like whether you use like a heterotheistic robust standard errors or you use like cluster robust standard errors, you're going to obtain you know, like a you know, like results on precision that are like radically different. Okay, so this could really change, you know, the nature of your result, your estimating precision. No? And the question is like, you know, which one should I use? Should I use this or should I use this one? Okay, and many times, you know, when people try to figure out which one they should use, they think, okay, perhaps yes, perhaps we have some correlation within states or something like that, and that's why we we want to use cluster standard errors. Okay, this is a problem in econometrics to the extent that, I can bet whatever amount of money you want me to bet that the most frequent question during my office hour is, should I cluster my standard errors? Okay, that's the most frequent question. The second most frequent question is, if I cluster standard errors, at which level should I cluster the standard errors? Okay, and unfortunately for me, I spent several years not having good answers about this, and up to a point in which we said we have to do something. Because we have to, this seems to be like a very basic question, but it seems that we don't understand exactly how to answer this question. And let me try to explain why we may not understand, or why we didn't understand exactly how to answer this question. In econometrics, and I think in statistics, there are two main models of a cluster inference, one that we call a model-based inference, for example, the data generating process could be something like that. You have your outcome, this is a parameter that you want to estimate, but you have some shocks that are happen at the level of the cluster. Okay? But you are not interested in these shocks in the data generating process, you are interested in mu. So you want that your variance reflect the variation in the shocks. Okay, that comes from this data generating process. So that's this model-based inference. There is also sampling-based inference, the usual idea that you may have perhaps many clusters, and you have two-stage sampling process in which first you sample clusters, and then you sample observation within the sample cluster. So the typical, at least in econometrics, the typical example of this, you sample families, and then you take perhaps all the individuals, within this family. Okay, you don't sample individuals at random, you sample households. Okay, so what are the problems with these two main models of a cluster inference? Well, the first one is in the first one, the researcher is going to be forced to take a stand on what is the error component that you have in the model. Okay, and this error component is going to happen in the superpopulation of data generating process. And if you are willing to do that, we have basically solved the problem. But the issue is that I don't know how to do that in practice. The question is why I should cluster perhaps at the state level, because perhaps there are correlated shocks at the state level, but I'm not clustering at the level of gender. Perhaps there are shocks at the level of gender. In fact, I will think that there are shocks along many dimensions. Why I should choose one and not the other, or why I don't choose 10 at the same time. Okay? And when someone comes to my office and asks me about this question, I don't have an answer. Okay? In the sampling-based inference, probably is that the conventional variance estimators that we use assume that we observe only a small fraction of the clusters in the population. But if the cluster has states, we are not using a small fraction of the cluster in the population. We typically are using all the states in the United States. Okay? And not only that, none of these two approaches is going to incorporate a moment for treatment assignment, and this is a semi-linear causal inference, and we are going to be concerned about the estimating causal parameters. Okay? And we need this a model of treatment assignments typically to obtain identification result for treatment effects. If we don't know how the treatment is assigned, typically it's very hard to figure out what is going to be the effect of the treatment. But also in the context in which we are going to use it, we are going to need to derive variance formulas that takes into account the uncertainty that this treatment assignment process is inducing in our estimators. Okay, so this is what we are trying to do. Questions? Please interrupt me at any point.
Okay. Alberto, in the Y cluster at the state level but not at the gender level, you still have to answer that question if you're doing sampling-based inference, because you have to determine the clusters at which to do two-stage sampling, right? None of these really get away from what are the clusters, which is really that question, right?
I will go there, but the thing is that let me go to the next slide to try to answer this question. So what we are going to do is the following: we will try to shift the focus of the interest not for features you find in an infinite superpopulation. We will not be interested in this mu that happens in some superpopulation of the data generating process. What we are going to be interested in the average treatment effect that we are going to define for the superpopulation at hand. Okay. we are going to incorporate a design component that is going to account for the variability induced in the estimator by the treatment assignment mechanism that I already said that. And we are going to accommodate settings where we observe all or a large fraction of clusters in the population. So like we think like perhaps, in these settings, we are going to observe, all the possible clusters, all the states in the United States. Okay, sorry, I thought it was here, but it's the next one, I guess. Okay, so when and how to cluster, okay? Like in the framework that we are going to think about, the decision on when and how to cluster is going to depend on information that is potentially available to researchers. Like institutional information that is potentially available to the researcher. It's like the sampling process and the treatment assignments, only those, they are going to determine the correct level of clustering. Okay, so I don't need to know anything about the correlation between the observations in the sample in the population. Like I only need to know, what is the sampling mechanism and what is the assignment mechanism. Okay, cluster sampling, of course, requires cluster sampling requires cluster inference. This we know. Cluster assignment is going to amount to cluster sampling of potential outcomes. We'll go to that in a second. And because the parameter of interest is a causal parameter, it's the difference in average of potential outcomes, cluster assignment also requires cluster inference. So basically, we are clustering we are sampling potential outcomes in a clustered way. Okay, and like this is like a presence of cluster level and observed components of the outcome variables is going to become irrelevant, for the choice of the clustering. So basically, we are going to be focused on two things only. What is the assignment mechanism and what is the sampling process? And if you know that, you can do it. Okay. All right, so let me try to go this in like a little bit more detail. Imagine that you have like independent samplings. We have clusters. Like let's say that each of these rows is a cluster of 5 observations. Typically, our clusters are going to be much bigger, but I need them to fit in the slide, right? But like imagine that imagine that you have any type of correlation. Imagine that in each row all these values are the same. I don't care. Okay, we know from basic statistics that if you sample at random, if you sample all these observations independently, like you're trying to estimate the mean in this population that has n observations, there is no need to cluster like the estimator of the variance. Okay. And again, you may have like a extreme correlation between this observation, but we are sampling each observation independently with some probability.
Expectation is going to be linear.
Okay, now imagine that again that you have the clusters. Let's say that they are families, but now you're not sampling like this observation at random. What you're sampling is clusters. Okay, like so perhaps you sample this one, and you sample this one, not the other ones, and then you sample this one here. Okay. Now, like if we want to estimate the mean, like in this population, again, this is the population mean because we only have n observation in the population. Okay, we need we have a cluster sample. We are going to need a cluster estimation of the variance. Okay, and we'll provide all the formulas later for the case of average mean effects. Okay, everybody happy with this, right? Like when we said, okay. Now, what happens with cluster assignment? The idea of cluster assignment is exactly the same. Imagine that you have all these clusters, but now, I'm going to code in red. I mean, imagine that we sample of all of them, and imagine that we assign all of them to either treatment or control. Okay, so what you have is like for the red clusters, you are observing the potential outcome with the treatment. For the blue clusters, you're observing the potential outcome with the treatment. So it's de facto what you're doing is like a cluster sampling potential outcomes with treatment or no treatment. And because the parameter of interest that you are going you are trying to estimate depends on the average of y1 and average of y0, like you will need to cluster the standard errors this way. Okay, so this is kind of the idea. Like we are not trying to focus on some parameters in some population. We are trying to focus on this parameter for a finite population. That the population is finite, as you will see, will be very important because we are going to think about cases in which we are sampling perhaps the entire population, or we are sampling a very substantial part of the population, or very substantial part of the clusters, perhaps all the states in the United States. And I cannot sample a fraction of the population if I have like an infinite population. I can only do that with finite populations. Okay? Okay, so we are going to demonstrate how this framework is going to produce precise answers on the properties of conventional variance estimator, and you can see also how to use it to improve this variance estimator.
Okay, so to apply this type of framework, you have to be very precise about defining specific things. Of course, one is going to be the estimate or parameters that you're trying to estimate, also your estimator, but also as you will see, we are going to need a sequence of populations because, we are going to be like a finite population setting, but we want to have like a Gaussian approximation in the limit. You will have to be like very precise about what is the sampling mechanism, and you will have to be very precise about what is the assignment mechanism, okay? And we are going to go like through this exercise for a particular setting. But like in principle, like you could do it in like in a much more generality. Okay. So what are going to be the elements of the model? Like I told you before, the first element is going to be a sequence of populations. We are going to have like a sequence of population that is indexed by k. Like a population k is going to have nk units, and each population is going to be partitioned in mk clusters. Okay, and MKI is going to be the cluster that unit I belongs to in population K. Okay, so the number of units in in cluster M or population K is hopefully it's like is not zero, it's bigger than 1. And for each I, we're going to have two potential outcomes, y1 and y0, and this correspond to treatment and non-treatment, and they are going to be bounded. We're going to think that they are bounded. Okay, and you say, okay, so it's a finite population, they're bounded. Yes, but we have a sequence of populations that are uniformly bounded in this sequence. Okay. So what we are doing here, we are conditioning the population. The potential outcomes are fixed, and the population is finite. As I said before, this is going to allow us to sample a non-zero fraction of it. But why we have this sequence? We have this sequence because we are going to embed this population in a sequence of populations. So at the end, we are going to have some type of limit, like a behavior of these estimators. Okay, so what is going to be the object of interest? It's going to be the average treatment effect in the population. This tau k. I'm also going to define alpha k, is the average outcome without the treatment. And we are going to use these two residuals that, please remember them because they are going to show up, quite a lot. So like this is like a UKI0 is the potential outcome without the treatment minus like alpha k. UKI1 is the potential outcome with the treatment minus alpha k and tau k. Okay, so like we kind of demean the outcomes. In each cluster, we are going to have also like an average treatment effect, and the average treatment effect in the population will be like a weighted average of the treatment effects in the clusters. Okay. Now, so far I told you about the non-stochastic features of this model. We are going also to have like a stochastic features, and the two stochastic features are going to be related to the assignment mechanism and the sampling process. Okay. These are the things that are going to be stochastic. For each unit in the population, we are going to define a stochastic treatment indicator. In this case, it's going to be binary, and the stochastic treatment indicator is what makes the outcome stochastic. Otherwise, it's going to be fixed if you fix W. And if you sample an observation from the population, what we are going to observe is we are going to observe treatment, we are going to observe the outcome, and we are going to observe the cluster that this unit belongs to. Okay, and if you are in the sample, if this unit in the sample, like this is going to be represented by this binary variable, RKI, that is going to take value 1, and if you are not in that unit is not in the sample, it's going to take a value 0. Okay, so now we have like two stochastic components in the model. It's like R and W, and like to define the sampling process and the assignment mechanism. We have to model these two. Okay. So let's start with sampling process. Like we are going to think about, like a simple, example. In this, there will be like a two-stage sampling process. Like clusters will be sampled with some probability. That can be 1, but cannot be 0 because otherwise we don't have a sample. And units also can be, like units in the sample cluster, are sampled with some probability that is bigger than 0, but but can be 1. And if we sample all the clusters, if Q is equal to 1, if P is equal to 1, we sample all the units in the sample cluster. And if the two are equal to 1, we sample the entire population, and our standard errors will allow that. Will allow for that. Okay. in the conventional framework for analyzing like cluster sampling and like in the Lian-Seeger type of estimators is focused in the case in which like we're sampling like a a small fraction of the clusters in the population. But at least in economics, in many applications, as I said before, are going to like entail the clusters are going to be something like a school district or like our state, something like that. And in many cases, we sample all of them or many of them. Okay. So we are going to refer to the case in which Q is equal to 1 as a random sampling, and the case of which Q is smaller than 1 is going to be like a cluster sampling. Like we don't sample the entire population, we sample some clusters of the population. Okay, so that's the sampling process. What about the same mechanism? The same mechanism also is going to be done in 2 stages in this case. Like in the first stage for cluster M in population K, there will be like some like a treatment assignment probability that is going to come randomly for some distribution with some mean mu and some variance sigma square. Okay, I'm not carrying the case when I speak because I get tired. Okay, and in a second stage, each unit in cluster M is going to be assigned to treatment independently with this probability that we sample in the first stage. Okay, and you can show because like this in between 0 and 1, you can show that the variance of the treatment assignment probabilities is between 0 and like a mu times 1 minus mu. Okay, so here we are going to have 3 cases. First is the case of a random assignment. So like all units in the population have the same probability of treatment. Like there is no difference in the probability of treatment. We have a case of cluster assignment in which a sigma square is equal to mu times 1 minus mu. And this is like the case in which all units that are in the same cluster, they are going to have the same treatment assignment. So if all units in the same cluster, either they are all treated or they are not all treated. Okay? Or they are all untreated, I should say. Okay, and finally we will have the partially cluster case in which like sigma squared is in between these 2 values, and here the treatment assignment probability depends on the cluster, but not but the treatment does not depend perfectly on which cluster you are. So like some cluster the treatment assignment probability is larger, and in some other cluster the treatment assignment probability is smaller. Okay. Questions on the setting? Okay, very good. So like we are going to have a number of treated units in the sample, number of untreated units in the sample, this is sample size. We are trying to estimate, or we are going to compute the OLS estimator. That in this case, if you don't have more variables, it's going to be the difference in means. It's just the mean of the treated, the mean of the outcome for the treated, minus the mean of the outcome for the non-treated in the sample. Okay, remember this is like this is the treatment binary indicator. This is the sampling indicator. Okay, so now we'll have to do like some assumptions in order to make this work. But if you make some assumptions, you have like a nice long like large sample results. The first thing that we are going to assume is that the number of clusters times the probability that a cluster is sampled, like this goes to infinity in this sequence. So like in expectation, the number of clusters is increasing with k. Okay. The second assumption is like the expected number of observations in a sample cluster is bigger than 0. Okay, so when we sample a cluster and we sample within the cluster, we have like some observations there. And finally, we are going to assume also that there is not a lot of imbalance between the populations of the large clusters and the small clusters. Okay, we don't want that there is some like very large cluster that is dominating all this. Okay, so like in this case, we are going to have like central limit theorem. We are going to have that the tau hat minus tau multiplied by the square root of the sample size and divided by some variance that evolves with k, converges to a standard normal distribution, and here is the formula for the variance. Okay, and now you see the formula and you understand everything, right? No, not really, but we'll go through it and we'll see what it's about. Okay, so let's start with the case in which you have random sampling, so q is equal to 1, and you have random assignment, so sigma squared is equal to 0. And the variance simplifies to exactly what you would expect the variance simplified, right? Like this, the usual variance that we will expect. Here you have the name and correction term for, like a finite population. Okay, that is exactly what we should have here. Now you add cluster sampling, so like Q is smaller than 1. Then this is going to increase the variance. Cannot decrease the variance, it's only going to increase the variance. Okay, and as you can see, the increase of the variance may be dramatic. Why? Because you have this nkm squared here, right? Like this is something that is going to increase very much with the population, with the size of the cluster. Of course, this is going to be equal to 0 if the average treatment effect in each cluster is exactly the same. Okay, but otherwise, this can be like a potentially very, very large term in the variance. Okay, so this is what happens when we add cluster sampling. What happens when we add cluster assignment? Well, we have these two terms, okay, that are multiplying like a sigma square. And these two terms, in principle, like they could be positive or negative, but in practice, like in most cases, they're going to be positive and large. Okay, so imagine that like potential outcomes. So this is like the mean potential outcomes. Okay, and then we are like averaging over all the observation in the clusters. Imagine that the clusters do not explain variation in average potential outcomes. Then this thing will be 0. We have something negative. Okay, but I go in there in a second. But if they do, like you can see that this is going to become typically, like a very large, because here what you have is like the square of the sum, and you have the sum of the squares.
I confess, I think I'm not quite following a clever trick, I think, that you've done, which is the sigma squared k, where defining that gives you cluster assignment. Could you go back to the slash?
Where we define that?
Yes.
Sequential assignment mechanism here. This is the variance of A. A is sampling the treatment assignment probability in the cluster.
And that's going to be the proportion of units, the expected proportion of units
assigned to treatment in the cluster.
And so if sigma squared k is bigger than 0, then that means different clusters have different proportions treated.
Yes.
But why does that give you cluster? Like you can imagine like a multi-site experiment where some clusters have 80% treated and some clusters have 20% treated. But within each cluster, it's still a simple random assignment of units. So why are you calling that cluster random assignment, rather than a multi-site experiment, for example?
Oh, you can call it that if you want. But what I mean is that the probability of treatment is different in different clusters.
Okay, but then you said that if sigma squared k equals mu times 1 minus
yes.
then everybody in the cluster has a treatment value? Has
the same treatment value, yes. Because this is going to happen with A squared is equal to A. And A squared is equal to A only if A is equal to 0 or 1. Right? Okay, and if A is equal to 0, everybody in the cluster has no treatment.
Right.
If A is equal to 1, everybody in the cluster is treated.
Okay, so I see. So you're defining an unknown distribution for AKM.
Yeah, it's totally undefined.
Then you have a consequence.
Yeah.
Okay. I think that is a trick.
Observation. If it is a trick for you, it's a trick for me. Yes, but what I wanted to say? Yes, like we call it a cluster assignment because the probability of assignment depends on the cluster, basically. Okay.
And then you're saying, so even if different clusters have different assignment, then you get a variance inflation because suddenly all of your units aren't being equally.
Yeah.
So you have this way.
It's a Bayesian thing. Like you're assuming the time distribution essentially is the point.
You could think about that in that way, yes. Yeah. So up to here we're good, right?
One last question. So all of this machinery is assuming that the proportion of units treated in the cluster is independent of cluster size. Like the A.
In this setting, yes. I mean, not all the machinery until starting here, right? No, starting there, right? And you can apply exactly the same machinery, changing the assignment mechanism and changing the sampling process, and then you will have a different variance.
Right. You have to finish off the math.
Yeah, you have to finish off the math. Exactly. Okay, but we think about this also like a kind of a conceptual umbrella under which you can put many different things.
Okay. Thank you.
Okay, so we saw what happens when we are cluster sampling. When we are cluster sampling, we also saw what happened. Typically this is going to increase the variance. And these are the conventional variance estimators, like the heterothelasticity robust variance estimator that is associated with the word of Aker, Huber, and White. The cluster robust variance estimator, like Lee and Seeger and Arellano in econometrics, have proposed this type of estimators. Here we have the sum of the square of the products. Here we have the square of the sum of the products. Okay, so that's kind of the difference between the two estimators. So you can go there and try to make some calculations about what is going to be the limit form of these of these estimators, and you can do it with the robust variance estimator. And when you do it, it's perhaps not very surprisingly, you are only going to recover the very first term, of the variance. Okay, when you do cluster, you recover many more terms. You recover almost everything, but there is something missing here. It's the term in Q, right? Because remember that this estimator is implicitly assuming that you are sampling a very small fraction of the clusters in the population. Okay, so we are missing this term in Q. Okay, so what is the comparison between the actual variance or the actual large sample variance and the robust variance estimator? So this is, we get this term, but not all this. And again, you can look at this, you can first take this term here that depends on the, the squares, of the difference of these residuals, and this other term here, that depends on the squares of the sum. Okay, and in principle, you can make this positive, negative. As I said before, typically this is going to be positive, and there are things that they cancel, very nice, or you don't have heterogeneity treatment effects. And the same is going to happen with this. This is the sum of the squares. This is the square of the sums, right? And unless you have things like these two errors cancel nicely, which typically do not happen in data, there is kind of this outcomes are somehow correlated within clusters. This term is going to be much bigger than this, and it's going to be much bigger. Again, it's going to be of a different order because here you're having a square of the sums over the cluster, and if you have many units within the cluster, in a state, and remember that we are summing in the population, right? This term could be really large. Okay, the difference between the cluster variance and the true variance in large sample is going to be much simpler. It's only going to depend on this term, and it's going to be equal to 0, as we said before. Is Q if Q goes to 0, it's going to be equal to 0 if you don't have heterogeneity in treatment effects at the cluster levels. If all clusters have the same average treatment effect, this goes away. Okay, but apart from this, and another thing that I should say, by the way, all these terms go to 0 if P goes to 0, right? Because they are multiplied by P. But this is the case in which you are sampling so few observations that it's very unlikely that two observations are going to belong to the same cluster. So in the large samples, these things go away. But this is kind of unrealistic. Okay, so if you don't have treatment effects that are constant across clusters on average, again, you can see that this term is going to be very large because it's going to incorporate the squares of the samples of the population sizes of the cluster. Okay, makes sense? So as I said before, and I say here, when Q is small or when the average effect of treatment is nearly constant between clusters, these two things are going to be similar. Aside for these special cases, the formula indicates that cluster standard errors can be and will be extremely conservative in general. Okay, and to solve this, we are going to propose two new variance estimators. One is going to what we call the causal cluster variance, and the other one is going to be called the two-stage cluster bootstrap. Not so if I like the names, but I didn't choose them. Anyway, so there is something nice about this. If you think about this, this is like the Neyman correction, but for clusters. Okay, like you have the average, the variance of the treatment effect across clusters. And the nice thing about this is for the usual naming correction, you basically cannot do anything about it unless you have like some covariates that are going to explain treatment effects. But for this you can, because as long as you have variation in the treatment assignment within cluster, you can estimate the treatment effect within cluster. So in principle, you can estimate this term. Okay, and correct. We are not going to do that. And we are not going to do that because if you try to estimate, if you try to put hats here and estimate this term, it's going to be extremely noisy. And it's going to be extremely noisy because it's a term of a very high order. Okay, so we will take kind of a backdoor in order to correct the variance. Okay, and you will see like how is this going to work. Okay, so if you do then, let's talk about the case with Q is equal to 1. So we sample of the clusters in the population, right? And you can make an expansion, and you can see the expansion there in the paper where this looks like very much like an asymptotic linear estimator. These terms, happen across cluster. These are cluster level terms. They have this form, and they are independent across clusters. Okay, and the usual cluster variance, what it's going to do is these are terms they are independent across clusters. What we are going to do is we are going to take the square of these terms and multiply by the square of this constant here. That's going to be our cluster variance. Okay, so the problem with this type of reasoning is that although the expectation of these terms across clusters is equal to 0, within cluster, these terms do not have expectation 0. Okay, and in fact, you can see what is the expectation. It's going to be the number of observations in the cluster times the sampling probability, and then mu times 1 minus mu, and the difference between the treatment effect in the cluster and the treatment effect in the population. So cluster by cluster, these terms do not have mean 0. And that's a problem because we are doing this to try to approximate the variance within cluster, but we know that the mean is not equal to 0. The second moment is not going to be equal to the variance. In fact, it's going to be bigger than the variance. Okay, and that's why we have like an estimator of the variance that is going to be too large in this case. So what we are going to do, we'll try to fix it in some way by subtracting some expectation of this term C. When you try to do it, I will not go over. I don't know how much time I have. I will not go over all the the description. But when you try to do that, you get into trouble because you are estimating different terms, and all these terms are correlated. And this is a variance estimator, and all these correlations are going to create errors for you. So we have to do some sampling split in order to estimate these terms and put them together. Okay, and when you do that, you can basically correct this variance estimator. So far, I told you what happens. All this was for Q equal to 1. Okay, but once you have Q equal to 1, you can do the same for any value of Q, because if you look at the formula, you see that the formula for BK with any value of Q is the formula for BK with a Q equal to 1 times Q plus 1 minus Q, the variance of the cluster estimator. This is, algebraically from the formula. Okay, so now what you can do is you can take, estimator for the new estimator for the variance is going to be the estimator for the case that Q is equal to 1 times Q, and the cluster estimator times 1 minus Q. By the way, something that is funny here is that there is nothing in the sample. I mean, you need information about what is Q that is outside the sample. The sample by itself, unless you know that you have 50 states in the United States,
But you don't know how many states.
you cannot say that, when we get 38 in this sample, it's only a fraction with certain value of Q. Okay, that comes from external information. Okay, but so Q, you need to know. Sigma square, you can calculate.
Okay.
Okay, that's kind of, there is a little bit of an asymmetry here. That's interesting. Okay, so that's one way to do it. The other way to do it is that, okay, perhaps everything is simple now, because now that you have a specified, a sampling process, and you have specified an assignment mechanism, you can basically bootstrap using using those processes, right? So I will not go over all the whole thing, but basically we are going to, like estimate the parameters of our assignment process, the parameters of the sampling mechanism or the sampling process, and we are going to calculate the standard errors in this way. Okay, so sorry, I don't remember when I should have finished.
About 15 more minutes.
15 more minutes.
15,
Okay, so
15 minutes.
I have also we have results for fixed effect estimators here. Like we have fixed effect estimators is estimators in which in the regression I'm going to include a dummy variable for each cluster, for each state in the United States. Now, my results are going to depend not on the use, but they are going to depend on the outcomes measuring the discrepancy relative to the cluster means. Okay, that we call E. Okay, and okay, so here is the result, right? I'm not going to go over this in a lot of detail. This is for a fixed effect estimator. This is the variance. It's going to happen exactly as before, you're going to have a robust variance estimator, a cluster variance estimator. The robust variance estimator is going to miss many of the terms. Okay, it's going to miss many of the terms, and it's going to miss the terms that are of higher order of magnitude. Miss the terms that can be really important. The cluster variance estimator is going to miss terms in Q. Okay, and that's going to be also a problem because those terms can be relatively large. Can be terms like this that depends on the square of the number of observations in the square of number of units in the cluster in the population. Okay, so how are we going to improve the estimator of the variance in this case? Now we're going to do something a little bit different. Here for some something that you can see in the algebra is that if you do a combination of the cluster variance and the robust variance, in fact you are going to eliminate the term that is the higher order of magnitude in the difference between the cluster variance and the variance that you want to estimate. Okay, and algebraically you can see that this is basically what you can do. You have to do do a convex combination of the cluster and robust variance with some weights. This is going to be the weights, and if you are asking where this comes from, well, remember, here we have this term in Q that is multiplying this sum, and again, this sum is of a higher order. Okay, and that's something that does not, this term in Q does not appear in the cluster variance. And doing this, a convex combination, we can get rid of it. Okay, so now we can go back to the college effects in the census sample. We have these two panels. Something that I should say is that for each of these two tricks, all these two variance estimators that I use, I need that in each cluster I have treated observation and untreated observation. Intuitively, we are trying to. Let me see. Intuitively, we are trying to correct for this term. And if we cannot correct it for this term, it will not be identified if we only have in each cluster, we only have either all of the observations are treated or all observations are not treated. Okay? And if you go to the definition of my estimators, you will see that you need you have both treated and untreated observations in the cluster. So when I go back to my original example, I said, yeah, in this case, there's something that if I'm going to cluster, I can do it in the second panel, but I won't be able to do it in the first panel. Because in the first panel, the treatment variable is defined at the level of the cluster. In the second panel, I can do it, and this is what I obtain. No matter whether you use which estimator of the variance, corrected estimator of the variance you are going to use, you get something very similar, for OLS, and you get something very similar to for fixed effects. And the nice thing about this is that these standard errors are much, much closer to the heteroscedasticity robust standard errors than to the cluster robust standard errors that are hugely inflated by the size of the clusters. Okay? So you get you make many empirical people really happy. Okay, so let's go into the simulation design. I don't know how much time you have. I don't have much time, but basically what I'm going to do is like, we're going to take like this data set, and this is going to be our population, okay? And from our population, well, we are going to calibrate the values of the, like average tree mean effect in each cluster. We are going to calibrate the values of the sigma square, and we are going to calibrate, all things like that, okay? And, we are going to create samples. Something that I should say, just for simplicity in this setting, within cluster, the tree mean effects are going to be constant. So like I'm going to define like a YKI0 as my observation, minus, the treatment effect that I estimate within cluster, minus the indicator of the treatment, and YKI1 is going to be my observation plus the treatment effect that I estimate in the cluster, plus an indicator of no treatment. Okay, I defined it in this way. Okay, so like when you take the, when you take the difference between two of them, like you will see that this is the effect of the treatment for each observation.
Why are there hats on the towels?
Sorry, I couldn't hear you.
Why are there hats on the towels?
Hats on what?
On the towels.
Because there are hats on the towels because, in each of these cases, I'm going to each cluster, and I'm, like estimating this average treatment effect in each cluster. And this is what I'm using as my, as my parameter of the average treatment effect in the population in my data generating process.
But you draw those, right? Don't you draw the treatment effects for each cluster from something that has sigma sub tau k?
No, this what we are drawing this if what we are drawing is like sigma square, right?
You also have a sigma sub tau.
Yeah, sigma sub tau. Yeah, yes, but that's going to be but you are not drawing it. It's like I will explain it in a second. So like this sigma sub tau k will be the variance of will be the standard deviation of the treatment effect across cluster, and it's going to have the value that we observe in the sample. Okay, and at some point we are going to say, what if we make this value bigger? And then we are going to make this like these two things like much larger. We are going to separate them. Okay.
All right.
But it will be like a constant treatment effect.
This was the hardest part for me to understand the simulation design in the paper. Was I thought you were drawing tau.
No.
Potential values.
No.
Okay, good. Go ahead.
Okay. So this is like the simulation result that we have. Like this is for the baseline design. What we calibrate, what we see in data is the standard deviation of the treatment effect across cluster is like 0.12. This is what we observed in the data.
This is not a parameter that goes in. This is an output. You observe it.
Okay. I observe it in my population, and I use this population to define a data generating process, to define to get more populations.
Okay.
This makes sense?
No, but go ahead.
Okay. I want to have a simulation. To have a simulation, I need populations, right? And I need a population, and then I need to do my sampling and my assignment mechanism. But I want my population to be, close to anything that is believable for us. Okay. So what I'm going to do is like I'm going to take the parameters of like the sampling mechanism and the assignment mechanism. I'm going to take for a population that I observe. Okay. But then I'm going to do simulation.
So your whole simulation is. You basically generated an entire schedule of potential outcomes for the United States.
No, it's not the entire because it's only for 2.6 million individuals. Yes.
All right. So, but you sort of you impute all the missing potential outcomes.
Yes.
And then you run your simulation by sampling.
Yes. So like once I'm going to estimate this in the population, I'm going to impute potential outcomes in this way, and then I sample or or I assign my tree. Make sense? It is I agree that it's a little weird because it's a parameter that we are estimating, but then we are saying this is the parameter in the population. We estimate this parameter, we adopt it, and once we adopt it, it's a simulation parameter. Okay, so I think I have very little time. Let me go like a little bit fast with this. So this is for the baseline design in which we are taking the values of parameters in the sample as a population parameters. This is the standard deviation. Like for OLS and fixed effects across simulations. These are the large sample, like standard deviations that we can compute because we know what is the data generating process, okay? And this is the, robust standard errors, cluster standard errors and the two alternatives that we propose. Okay, what you can see immediately is that, in this case, both the robust standard errors and the cluster standard errors are too integral. Okay, this is too small, way too small, and this is way, way too big. Okay, you can be conservative, but you don't want to be that conservative. Okay, and
This is the design where all of your states are included and all of your individual.
yes. Here, Q is equal to 1, and P is equal to 1.
And so the only randomness is the random assignment of units.
Yes. Yes. So, go ahead.
It shouldn't be surprising, right? Because they're robust in the cluster, they're not, like they were derived from the sample base perspective. They weren't derived from this perspective. So it's not
That is fine.
surprising it's wrong.
That is fine. No, it's sure. Like you say, again, like I'm thinking about, some parameter that I'm estimating a superpopulation. In the case of the cluster standard errors, you say, I think that in this data generating process I have these errors that I want to take care of. That will and because it's an infinite population, my sample is always, like a very, very small fraction of that population, like a fraction of size 0. Like then the cluster standard errors will be great. But then the problem is that I cannot tell you how to cluster.
Yeah.
Okay, so what I wanted to do is like something that I can tell you, you should cluster or you shouldn't cluster if a student come to my office, and I want to tell you at which level you should cluster, and then I want to have like a variance.
Yeah. It's just not that surprising that the robust and the cluster ones are, one's very much under, one's very much over.
I'm surprised by the robust one because all of the states are represented. So that means that you have estimated impact for each state, and your overall estimate's precision weighted average as well as individual estimates. So I'm actually not sure why the robust standard error estimator comes in.
You're going to make me go back.
Yeah, when you write it.
So here, right? You remember what we said about the, this, okay, let's go here. This term, this depends on the, the variance of the assignment probability. Okay?
It's a variance of the assignment probability.
Yes, and this is not zero. It's not zero in our simulation.
You're treating a different fraction of units within each state.
Yes.
But
on average.
With fixed effects, you should still get a precision weight. Like the fixed effect should.
No, you don't get it. You don't get it. Fixed effects, like a fixed effect, you wouldn't get something. Fixed effect, you will get.
Fixed effects handle different probabilities.
Fixed effect, it will go great if you are in this model. This is where fixed effect shines, right? Because you are taking into account all this variation. And there is nothing about, the sampling mechanism, the assignment mechanism, all the clustering comes from here. And you're taking care of that with the fixed effect. But, in my case, all these y's are fixed. And all the variation comes from either sampling.
I understand that. And I thought I had thought through all of this before in some work I've done where I ended up concluding that if you're conditioning on the clusters you have, that robust standard error, because you're basically simulating a multi-site randomized trial.
Okay.
Where each site is a state, and you have a different fraction of people treated within each state.
Yes. But I have something else. I have something that I'm using as the identification condition is that this A on average is the same for all the states, because otherwise I'm going to have a bias. These different states have different assignment probability.
A is on average. Okay, so you're changing the probability of assignment within each state.
Yeah, but has the same marginal.
Whereas with the multi-site, I'm conditioning on if you condition on the fraction of units treated within state, your robust standard errors are fine.
That may be the case, but here we are not doing that. Yeah.
It's the randomness of the proportion treated. Yes. Which is actually interesting because it's a different randomness than the assignment mechanism itself. I would.
It's at a higher level the same one.
You see that in the fifth design. Exactly what you're saying, Luke, is that sigma sub k equals 0 in the fifth design, and then the robust are fine.
The robust are fine here.
Yeah. What's interesting though is so sigma sub k being 0 means that all of the states have the same proportion treated. Yeah. What I'm saying is that if you hold the proportion of units treated as fixed but different for different states. Like California is always 60%, Wyoming is always 20%. The robust standard errors will also be fine.
Kind of what different.
I mean, that's your conditioning. Your conditional difference.
Yeah, so actually that's why I prefer the robust standard errors in the context of a multi-site trial.
It's only compared to how you value.
Yeah.
We would value this scenario that ones makes more sense.
Okay, so let me see how long I have. I am out of time, but basically.
5 more minutes, maybe, just to wrap up.
So you have like a standard errors that are too small here, too large here. You know, like when you decrease P, so like you don't sample all the units, things become a little better, right? Because, you know, like as P goes to 0, like, you know, like all these standard errors, like a cluster and robust are going to do well. They do better, but, you know, they are still far away from the values, like, you know, like our variances do quite well. Here, what we are doing is like, we are taking these parameters, so basically multiplying them by 4. Like, in fact, for sigma, you know, tau, we are, you know, in fact, multiplying it by 4. For here, we are multiplying something else by 4 that produces this. Okay, and yes, and like, and things in that case, in fact, becomes much worse both for the like, you know, like a robust and for the cluster. And this is like finally we're going to have what you were saying, right? Like when we make like, okay, we're going to have like a variability in the assignment probability, but not in the treatment effect. Okay, the cluster standard errors do super good because you remember that they were only biased because you have variability in the average treatment effect across clusters. Okay, and when it's the other way around, the robust standard errors are going to be good because the main bias there was coming from this sigma square. Okay, so like that's the way it happens. But in all cases, like you know, like our variance estimators are going to do well. I cannot say much about you know, coverage rates. Anyway, let's finish. Like so, what we are trying to do is like we are trying to not be totally embarrassed and have something to say when people come to our office and ask us about, hey, you know, at which level I should cluster standard errors, and this has happened in my life many times. And because, you know, like we don't know how to do it for the population model, like what we do in this paper is like, okay, let's shift attention to something else. And let's think about, you know, the finite population treatment effect. Okay, what happens in this population that is finite? And, you know, like you may sample like a part of the population. Okay, and this, you can see that in this case, only the sampling and the assignment process are going to matter. The presence of within cluster error components is not going to matter unless you go to the, and they are such that, you know, they are going to, certain things are going to cancel like perfectly. We are going to derive expression for the large sample variance. We demonstrate that robust standard errors can be too small and conventional cluster standard errors can be too large, and we produce like some new variance estimator that's correct for that. And as I said before, these variance calculations are for this particular setting, for this particular assignment mechanism, for this particular like sampling process. But you know, like you can use the framework to like generalize to other settings. Okay, and in fact, there are like people like doing that as we speak. Okay. So thank you very much, and thank you for.
Maybe should we have 1 or 2 quick questions before Laura?
In your paper with Spice on robust inference for post-matching, robust post-matching inference, after you've done one-to-one matching and you're fitting a regression model, you also recommend cluster robust standard errors where you cluster on pair membership.
Yes.
Does that fit into this framework, or is it completely separate and just happens also to work out to be the same estimator?
To estimate like these are like a very different framework. We're talking about a different paper. This is a different framework because we're trying to estimate the average treatment effect in a superpopulation. Like, and you have like you don't have this problem that you are like you know, sampling, you know, things, you know, like you are sampling a significant fraction of the population, and in that case, we know that these robust standard errors are going to work well.
The cluster robusts.
The cluster robust standard errors are going to work well. That's okay. But it's like case in that paper is like we are first like matching observations. Like we have like treated and untreated, and we are matching. For each treated, perhaps we get an untreated and something like that. And then we run a regression on the match sample. And the question is, does the, like a matching process in the first step is going to affect the standard errors that you are going to calculate in the second step? And you can see that you can fix those standard errors using the cluster robust variance. There was another question.
So here you're basically assuming the clusters are completely separate. Have you started to think about what is this? Okay. That was quick.
No.
It's a similar story if you have like a network.
I was listening to you. The level of my fear was rising. No, I don't know. I don't know how I will do that. I think it's a great problem.
Yeah.
But it's not solved, by what we have in this paper. But you're thinking about kind of like network.
Well, you have a network, and like the design-based approach has blown up in analyzing network data, but there's still no clustering, and it's very much, we have some sort of randomization, and we do like an IPW estimator, and everything works out well.
And you sample the network?
There's no sampling, so you're basically saying there's no notion of the sampling. Typically, in most of the papers I've seen, you basically say I have the full network. And I randomize everyone into this network.
Yeah.
But it'll be interesting because there's a lot of examples where you do just sample some small portion of it.
Yeah.
Like if you're thinking like a tech company, they'll have lots of customers, but
Yeah.
you're not going to see all of those customers. You're going to sample them.
Yeah.
So
Yeah, I was thinking also in cases in which the assignment probability may vary, like
Across clusters, absolutely.
in a like a smooth ways, in a space or in time or something like that. We didn't think of
Okay. Cool. Well, so PhD students listen to this. With follow-up project.
I also have a question. I don't know if this is something that you have thought, because that's a question I get asked all the time, and I don't know the answer. So very similar setting, but on top of that, you have a propensity score. And the propensity score so let's take for a moment that you have the treatment assignment is at the cluster level, and you're also suggesting for confounding. So the question is, do you propagate uncertainty when you're estimating the variance, right? Are you assuming that the propensity score, the propensity assignment is known, or you are propagating the uncertainty of the estimation of the propensity score into the variance estimation of the causal?
Okay, so there are two ways to answer this question. One is in this design framework.
Yes.
And the answer is we are working on that.
Okay, good.
Okay. And the other one is like in more of a like a superpopulation type of framework, and in that we we know that it yes, like a estimation of the propensity score is going to affect uncertainty in the second step. In fact, we know that depending on which parameter you estimate, but typically, for example, especially if you estimate the average effect of the treatment and the treated, you should estimate the propensity score. Even if you know the propensity score, you should use to estimate the propensity score for the large first order.
But you also propagate the uncertainty?
Yes.
Of the propensity score?
Yes.
That's different from, Don Rubin used to have very different.
Yes.
Well, right? Because he would say that you try to approximate a randomized trial, so there is just one proportion to approximate the trial. So.
Perhaps he was.
That's why I'm always. So I see your argument, but also see his.
Perhaps he was thinking more a design, like a framework.
Yeah, you have a design phase, you have an analysis phase. So you have just one design.
No, a design framework for calculating these variances, which is what we are trying to do now.
Okay.
With covariates. What happens when you do in a superpopulation? You can think about. Okay, so like you have. Let's say that the propensity score is parametric to do things right. Okay, so like you could do like an asymptotic expansion in your parameter of interest, but you're going to have something that is not asymptotically linear because you have all these parameters of the propensity score that are estimated there in the influence function that is not an influence function. So you want to do like another expansion there, right? But what you're going to find is that this other expansion matter, that the that the geometric of cross derivatives is not going to be equal to 0. And it matters because estimation of the propensity to occur in the first step, unless, or let me put it this way, unless you consistently estimate the propensity score, you cannot estimate consistently the second step parameter. And because of that, you have to adjust. And because of that, this matrix of cross derivatives is not equal to 0. And because this matrix of cross derivatives is not equal to 0, you're going to have an extra element in the influence function, and you should adjust your standard errors. I should do this Blackboard, but then.
No, but thank you.
Yeah.
Great. All right, so maybe should we take like a 2-minute quick break and then set up? And thank you so much, Alberto. As you hopefully most of you know, we usually have 2 discussants after Alberto. Feel free to just grab a seat. So our first discussant is Laura Hatfield, who's an associate professor at Accounting and Policy. So thank you so much for agreeing to do this. It's super excited that you were able to join us. So please take it away.
Great, thank you. So I've given my talk a very lofty title today, the multiverse of uncertainty, and it's basically because tonight I have tickets to go see Quantum Mania, really influenced by the Marvel Cinematic Universe, which, as you know, has successively ratcheted up the stakes of superhero movies by going, it's not just Earth, it's not just the galaxy, it's not just the universe, it's the multiverse. It's at stake in every single movie now. And the concept of a multiverse is resonating with me because sometimes my experience of being an academic researcher is that I operate in a universe and then I encounter a version of myself from an alternate universe where people care about totally different things. We all think we're doing really good causal inference, or we think we're doing really good statistical inference, and it turns out that I've spent my whole life thinking about a particular form of uncertainty, and I've been ignoring spatial uncertainty. And over here in alternative universe, all they think about all day long is spatial uncertainty. So that's what it sometimes feels like to me. Today, I'm going to talk a little bit about the context in which I see Alberto's very excellent work. To me, there are fundamental questions that inference, and I mean inference both statistical and causal here, but let's talk about statistical for just a second. How do we quantify our uncertainty about the quantity of identifying information that we have? And I say identifying for a very specific reason, right? It's not just the number of rows in our data. It's the number of rows in our data that are informative about the thing that we're trying to estimate, our target estimate. And the quantity, the effective quantity of the information that we have is reduced by dependence amongst the observations, right? 2 units from the same cluster don't count as 2 totally distinct bits of information if there is, within cluster correlation. There's also something about the quality of the identifying information that we have observed. So if we have mismeasured something, some of the X's, some of the Y's, then we have also reduced sort of our ability to identify the thing that we care about. So there's quantity and also quality. And then there's the relationship of the stuff we have measured and the identifying assumptions we've made and the design that we've assumed to the thing we actually care about, our target estimate. So model misspecification and bad identifying assumptions are all things that would go under this heading, and maybe the wrong target population. We've identified something in a sample that is not relevant to our target population. All of those things are the kinds of uncertainty that one might try to incorporate into our eventual estimate. And it's uncertainty all the way down. So if you Google multiverse in Google Images, this is what comes up. So suppose we start out with something as simple as y equals x beta plus epsilon. We're interested in beta. It's the causal, let's say, impact of x on y. Here's what I mean by the places that people focus their time and energy. Over there in the error term, epsilon, we could think of that as encapsulating just measurement error or maybe just sampling error, but let's call it measurement error. And there's like a whole world of people who spend their time just thinking about the variance of the epsilon term. Maybe we could call that classical statistics. There's people who spend their whole careers just writing papers about the dependence structure amongst the errors. And some of those are dependence across time, dependence within clusters, spatial, network. You were sort of starting to ask about network structure. I think this fits into this broad class of research about clustered standard errors. But I've encountered a lot of economists, and it seems like they don't care at all about hierarchical modeling, and that was my whole PhD training, and I feel so sad about it. There's also this problem of the target population's relationship to our sample population, and there's the whole world of sampling statistics, there's a whole world of transportability. How do we take an estimate that was obtained in one sample population and transport it over to make inference on another target population? We talked a little bit in this talk about finite versus infinite populations. People who spend their whole lives thinking about errors in covariates or mismeasurement of the treatment assignment itself. And then people who talk about the heterogeneity of the treatment effect estimate. Is there mediation going on? Are there subgroup effects? There's a little bit of that in this paper, which is the variability of the treatment effect across clusters. And finally, the model misspecification question, which there's a whole world of people writing model averaging papers, for instance, to capture our uncertainty about the y equals x beta of the whole thing. Like, what if that's wrong? What if it's y equals x beta squared or something, you know, or it's a complicated nonlinear function. So all of these people all across the multiverses of statistics and econometrics are studying how to quantify the uncertainty, and we're just picking off just like two pieces of that in this paper that Alberto presented today, which is the sampling mechanism, which maybe sampling statistics people have something to say about, and the treatment assignment mechanism. So I also appreciate that this is not the first paper that I've read that is dunking on robust standard errors. So I found a couple of other papers in the literature that are doing a similar thing. King and Roberts in Political Analysis, our good friend Gary King here, published this paper that said, first of all, it's really cute that you can fix up the standard errors on your beta hats, but that is not enough, because there are lots of kinds of inference that you might want to do that require you to know the whole error structure of the model, and it's not good enough to just fix up the standard error of beta hat. So do better. In particular, because if your classical standard errors and your robust standard errors are very different, it indicates that your model is wrong. So why should we trust the rest of the model? Just because you fixed up the one little thing that was wrong and you got your standard errors correct on beta hat doesn't mean we should trust you about anything else. So their sick burn at the end of the paper is, okay, fix up the rest of your model. Do it so that it doesn't matter now. There is no difference between your robust standard errors and your classical standard errors because you've fixed all the problems with your model. Wow. Mic drop. All right, second paper dunking on robust standard errors. Freeman, 2006, in the American Statistician says, don't blame poor Peter Huber for this ridiculous idea called Huber sandwich estimators. This poor person should not be blamed for the misapplication of this sandwich algorithm, as he calls it, because even if you can fix up the standard errors, you're doing it on a parameter that doesn't mean anything. So it's kind of a similar point that Gary King was making, which is like, don't worry about fixing up the standard errors on a thing that is itself wrong. Okay, I think that's what it's called. Both of these papers, dunking on robust standard errors, were a joy to read. I also noted that this proposal for your two-stage clustered, robust bootstrap is in a tradition of a bunch of clustered bootstrap procedures, and I wondered if you see yourself as in conversation with any of these proposals. For instance, there was a big comparison in JRSSB of 6 different bootstraps for clustered data. They all have names that make them impossible to distinguish, and I think TCSB would fit really well. You were uncertain about the name, but I think it looks like it belongs exactly.
Me too, better.
So here's my interpretation of tables 2 and 3, which you just showed us. Down in scenario 4, perhaps clustered standard errors might be fine when there is no across-cluster variation in the treatment effects. That the robust standard errors might be fine when there's no across-cluster variation in the treatment probability, that A or the sigma sub k. And that the new methods that you propose are totally inapplicable when you don't have within cluster variation in treatment assignment. You have to have treated and control in each cluster to do both the CCV and the TCSB methods. So it seems like, to me, you need all 4 of these things to be true for the new proposed methods to be advantageous. You have to have that within cluster variation and treatment assignment. You have to have a cross-cluster variability in the treatment probability. You have to have a cross-cluster variation in the treatment effects, and you have to have large enough clusters. I think this came later in the paper in order to do a good job of fixing everything up. So this is where I'm getting those ideas that, cluster seems fine in this situation and robust seems fine in this situation. So you sort of need a bunch of things to be true to make use of the new two proposed variance estimators. So my questions, just gonna go quickly, are, I retract this question. I now understand what a sequence of populations indexed by k means. It means we needed a way to do large population inference without letting n go to infinity. We're gonna let k go to infinity instead. So never mind, I understand why you did this. In the paper, you talk about the dependence of the model-based inferential methods on committing to a belief about the error structure. And I was very influenced by this book from Hodges, who was one of my thesis advisors, who wrote a book about how random effects can be conceived of outside of the Lang and Ziegler notion of infinite populations and making inference on a superpopulation. Instead, we can think of them as like a convenient shrinkage technology that is applicable well outside of just the domains of old-style random effects, for instance, which say you're making a sample from an infinite superpopulation worth of state-level effects or whatever. So maybe we can expand our minds about that a little bit. I'm also so curious, in the table that you showed about the state-level greater than 0.55 proportion of some college, why aggregation is so unpopular despite many papers that have recommended it. So I know that you are aware of the Bertrand paper. You may not know this Rokicki paper, but a lot of these are saying, like, as long as you don't have within cluster variation and treatment assignment, just aggregate up to the cluster level and do everything at the state level. And your inference will be easy. And I'm so curious, so I'm a policy person, and so almost all of the time when we have clustered assignment, it's because an administrative unit enacted a policy. And so there's almost never treatment variation within clusters. So states enact laws and we study those laws, or hospitals adopt policies and we study those hospitals. So I'm curious where in the real world you think we can see situations where we have the within cluster variation and treatment assignment, and there is a cross-cluster variation in treatment probability, and there is a cross-cluster variation in the treatment effects. Like, help us imagine that situation. And then finally, this is kind of a cultural question. Defaults are so sticky. People get stuck in their analytical ruts. And I have been making fun of comma cluster for the last 5 years. This is Stata's contribution to this problem. Just comma cluster, right? I saw it in when I was a Bayesian, this gamma epsilon prior on variances. People got stuck on it because it's what WinBugs did. P less than 0.05 is like the worst offender of some kind of analytical rut that we all got stuck in. I think two-way fixed effects are my new dumb thing that everyone's sort of got in the habit of doing. So I'm curious how we get people to change those sticky, bad analytical habits, and perhaps you're compelling us to stop just using cluster unthinkingly or robust standard errors unthinkingly. So that's what I've got. Thank you.
Alberto, you can quickly respond if you have any
sure.
answers.
First, thank you so much for all these comments, and that is going to give me a lot of reasons to think about new directions to go. I will not try to answer everything. There is a lot of stuff. Something that you say that I want to address is the following: like you need like a certain this variability, and you need that variability. So like you need variability in, you need sigma square like bigger than 0. You need Q smaller than 1, and you need variability in the treatment effects and across clusters, and you need to have like a treat and non-treat observation within cluster in order to apply your methods. I think that is I will not characterize it in this way for the following. First, yes, the result says that if you have sigma k equal to 0, or you have sigma tau equal to 0, like you can use those, those other variance estimator. But that's the result of the analysis. Like that's nothing that we knew before. That's the result of the framework. So like the framework is telling you like there are in some cases in which you can use these estimators, in some cases you cannot use it. So I think that this is, I would say that this is a contribution to this, and it doesn't say okay. So like, and in some cases you won't be able to use the new proposed variance estimators, which by the way I don't think this is the last word in what people are going to say about this, because this is for one particular sign mechanism and one particular sampling process. But I think like in I guess not in your world, but in my world, there are many cases in which like we have large clusters with we have like school districts that have like some kids that have in the like some special programs, and some of the kids are not. Like and the proportion of this like the number of kids that are in the in this particular program is different across clusters. You have like states in which you have different levels of protection in the labor market that are going to affect the treatment of all these workers. So we have many of these instances, at least in economics, and we have like clusters, like the effect of the treatment, the treatment probability by cluster, but not all the people in the same cluster are treated and untreated. And that's also like a kind of a you and Luke are purely in different directions. So I don't know where to go, because Luke is only mean. So this is about the multi-site randomized trials, right? And it's the case in which you have like different places where the assignment probability is different. And you're telling me that no, like in each place you have the same assignment probability. So I guess that perhaps in the middle somewhere.
Yeah. Well, you should listen to me then.
All right, so brilliant, thank you. So next we have Xiaoli Meng, who's the title Whipple, V. and Jones Professor of Statistics. So thank you so much for agreeing to do this. Let me give you the clicker. It's this one. And please take it away.
All right. Thank you very much. I somehow saw this discussion would be 10 days from now. And so yesterday when Ira wrote to me say, and I'm ready for tomorrow, I said, holy cow, and it's today. So my apology that it will be long because I don't have time to write a short one. And it's literally true. So I also thought I was glad to hear that I'm the second discussant, because in statistics there's this tradition that, like a JRSV, you have this tradition. The first discussant will be very, very nice, say all kinds of nice things. The second discussant can be as brutal as the person wants. But unfortunately for me, I think Laura is already pretty critical. Oh, no. Basically, you're saying you're working on a tiny bit of problem. There are so many other problems to work on, right?
That's not what I was thinking about. The whole thing is great.
Yeah, and I would agree with you that but the only thing you need to remember, that tiny problem. There's only one universe you can get a Nobel Prize. The other problems you can't.
But I have to say that the next paper I will solve all the problems.
Well, okay, then I will get to my talk bit. I will claim that because I'm doing divine probability, I do have an approach to solve all the problems, okay? Now here. I guess this will be long because I'm just getting jokes, right? That's fine. We have what, to 6 o'clock?
Yeah, like 7, that's fine.
The other thing, I was very happy to do this discussion for a paper written by economists, because I heard economists tend to be very, very tough with each other, right? I heard you guys going to give a talk, somebody give a talk, then 10 minutes in a talk, the talk has stopped, and the person will be asked lots of questions. But I just want to show that statistician can be tough too. Now here's an example that from this JSB discussion. Is this the one?
That's the one, yep.
Okay, see if I can move it.
There you
go. All right, this is from one of my ex-colleague, Peter McCulloch. Yeah. He was a discussant of a paper, and he said, the parts of the paper that are true are not new, and the parts that are new are not true. Now, whether I will apply this to this paper, you will see at the end. Now, first, let me seriously explain what do I mean by these terms. coined this term divine design device because I was asked to be a commentator for another paper talking about how to analyze non-probability sample. And so first I want to understand what does probability sample means, right? Because everybody talk about probability, but then it occurs to me that it's useful to have some terminology, and I think it's quite applicable to this paper. So let me first say I was also particularly pleased to see this paper, Alberto and authors, explicitly using the R, right? The indicator, whether something is in and out, because that's a standard finite population calculation, and that's very important. Most statistical courses don't teach that because you treat the variables at random, you don't treat the R's. So I was very happy to see all the finite population, everything's fixed except the assignment, but you have two of them, which is very good. One is the R, one is the W, which is the assignment. Okay, so that's what I've been using R as a very generic term, so of course, they're thinking with R because everybody loves R, but this is different R. So I use R as this kind of all-catching. I use the word recording. Essentially is whatever the process is, in the end, your thing is in the sample. So if I could do 1, you're in the sample. I could do 0, you're out, okay? So that's a simple setup. Even this setup itself can be questioned. There are cases where it's not even clear whether R itself is no, but we're not going to get that complication. So, but when we think about these, these probabilities, that when we talk about R as in and out, if you think about these days with all the media data, social media data, it's not clear whether you can even assume R is random or not. Okay, but when you don't have a mechanism there, R just R. It's whether you're in and out. So I think the kind of stuff we love to do, and I think economists love to do as well, is what I would call design probability. These are the probabilities that we implement. These are probabilities under our control. Sampling, random assignment, bootstrap, a clinical trial, differential privacy, you add a noise to it, permutation test, Monte Carlos. These are all the probabilities that we have control. We can do all kinds of things because at least we should be able to do all the calculations. So I think Alberto's paper is really a design, or you can call finite population, but I think it's more important to recognize that this is a design probability. That's the where we do best, okay? Now I want to introduce this concept, which is probably new to you, and I want to convince you that it's a very useful concept. I call it divine probability. What does it mean is, one way you can think about it's a property given to you. It's probably existing in the nature. It's true. Or you have the faith to believe it's true. You have the faith to believe it existed. I would tell you exactly what I meant by that on the next slide, and you would agree with me that is a very useful probability, and it's entirely true, no model assumption whatsoever. But here is the question: where is the what's the pointer?
It should be the middle.
Oh, the middle one.
Yeah. Okay. Like pointing up.
Well, it doesn't matter. Let me use my hand then, since I'm loud enough. So here, for example.
So see that button right there?
Oh, I see.
Up there, and they point like
Okay,
that.
okay,
So
thank
push
you.
that button up there.
Thank you. Okay. Some of you may have heard we talk about these missing at the random all the time, right? When we model this R. Well, the very notion you think about it's missing at the random, you already assume it has a random distribution. The randomness is an assumption. I'm not talking about particular distribution you take. Just the very assumption that is random is an assumption. You have to, without that assumption, you cannot even talk about all the down loopings missing random because there's a framework distribution, so on and so forth. And the one we tend to all use all the time, right? And that is the one we tend to use all the time is what I call device probability, which essentially is the model-based. These are the probability we use as a device. We don't really believe them, okay? Now, when we do logistic, we do normal, we do all kinds of stuff. We don't really believe them, but they are very useful as a device to help us to derive things, to get all those things going. And I think that the part of thing, particularly for students, for this particular paper, when there are these two different probabilities being used, one is all the design probability, the sampling mechanism, and the assignment. The other is all these model-based, right? These probabilities are very different. Okay, there's no particular reason that we shouldn't even compare them, because they're sitting on very different space. But I think at the practical levels, in the end, we all talk about uncertainties. we kind of forgot they're really different animals. Sometimes we see them being, being very different. But so what I want to really kind of recast the paper in the following version. I think what the paper is set up is really a squarely kind of design property set up. And so you have, I'm going to use one population, okay, just for this purpose. I know you have a sequence population, but everything I said, it goes with more. So you have a particular estimate can be written in this version, which is like a population average, right? That's your version. And your estimator can be written is a sample average. In this case, is two sample average, a difference between two sample average. And the most important part, you need to write the denominator as the sum of this indicator instead of the n. Now I know you make sure it's not 0 to be having a 1 there. And for me, that all the calculation will be conditional on the denominator is bigger than 0. So that's achieved. Although for practical purpose, if it's a 0, then you don't do it, right? Because you have nothing to work on. But theoretically, that is is important to consider that. So this is the estimator. Now, so here you have a bunch of indicators, and I want to be explicit about it. You have these R's. I use 1 and 0 to point out that 1 is the entity assumption of the first treatment, which treatment, the other is not treatment. So essentially, you have a cluster sample indicator, right? Whether the cluster I belong to gets sampled, because I can get sampled only when the cluster gets sampled, right? The second, within the cluster, you have a unit sampling, right? Within the cluster, if I get to choose. And then you also have that if I get assigned to this particular treatment, right? The reason I want to do this is each one of them is 0, 1, okay? And the product equal to 1 if and only if all of them equal to 1, right? And that's the whole thing. That's the whole thing. Now, what's going to get complicated is because you have all these different assignments. Like in this particular case, in the paper set up here, that all of them, although it's complicated, but every one of them, we know the property distribution because you are the one assigned to it. So you can see in principle, I can do all the calculation, right? Minimally, I can have a graduate student to work on this, okay? These days, I might even ask a ChatGPT to do it, who knows, right? But you can see this is a very clear setup, okay? It's a classical setup. Because entity setup, we can calculate all these things, right? So now the variance is derived, entities property mechanism, whatever you assume, right? Now, so my kind of, you can take that as a critique, but it's not a critique to you particularly, it's a critique to the entire statistical profession. And it exactly is Laura's point. Now, real life is far more complicated than this. It's far more complicated. Now, I'm not even going to talk about all the things you talk about, all these universe. Let me just pick up a couple of very standard things that I think that, I know you all deal with it, but I just want to make this explicit for the graduate student here. Let's see if I can get right. So at least if you think about just with this very simple sampling and assignment mechanism, you also need the device property. What do I mean by that? Okay, now you still have these R's, but now the R is a multiplication of a 5-factor instead of 3. Okay, the first 3 you already see. But what is the other O? Well, O is just because you sample somebody doesn't mean that person will participate. This is a very standard non-response mechanism, right? So at least you need to O. Now, if everybody responded, your O equal to 1. Otherwise, you have another indicator. Okay, number 1. Number 2, just because you assign somebody to the treatment, the person is not going to follow your treatment. And you guys know this well, compliance is problem. So now you have another one here, right? And then you also need to worry about the compliance will be different depending on what treatment you get assigned. Somebody say, hey, I'm happy to be in the control ones. Maybe I'm not happy to be in that one. Now, how would they know? Who knows, right? Because you got the side effect, so on and so forth. So you have to be careful notation-wise. Now suddenly you already have 5, right? And it's the same game because in the end is whatever there is, will that be equal to 1, or will that equal to 0? Now here we'll say these two, no matter how careful you do, they're not end-to-one control typically. Whether people participate or not, whether they follow our treatment or not, right? And then we'll be doing all kinds of propensity score matching, do all kinds of modeling. And this is where I call the device property comes in, because you no longer can do this randomization inference, but you do. So in the end, in this case, that if you really want to take, so now you will have like a mixed probability calculation, right? There are some design probability calculations, which you already have done clearly. But then if you want to do additional one, you have other probability calculation. And you have seen, even just doing the design probability calculation is pretty long as well. And then, now you have all these things. Although, by the way, for people looking for thesis, every factor is another thesis. I'm not kidding, right? Because that's all the problem. Now, my point here today is that I want to really emphasize that as much as we statisticians, economists work for all these years, do all this great work on these sampling variability, things we know, that is really the more negligible term compared to everything else. So I'm going to give you I have a way to specifically formulate this thing and to show why we should pay a lot more attention to factors like these, because these are going to kill us, okay, in terms of the kind of variability. So where is the divine probability coming? Well, I claim that there is one way to look at this problem, and some of you know, I know Francesca know my work, 2018, I think I'm going to talk about that. So how do you utilize the fact that you were given a finite population, right? Anytime you give a population, you have a probability. You have a histogram. You use that probability to measure those things. And I'm trying to convince you that there, at least to provide some good insight to look at these problems, okay? So now, this is what I call the divine identity. I used to be called fundamental identity. Last night I said, well, why do I call divine identity? Because it's using divine probability, okay? So I'm going to switch to the generic notation. I know Alberto's paper is about average, 2 averages. Well, you can write a 1, but here I'm just going to focus just on 1 average, okay? So here's your estimate is a population average, okay? Now, your sample average, we're going to use this trick, using this R indicator. Now, remember my R here is a product of many things, but I don't care what it is. And for this level, I could do R. So you can write this, right? Now, here is the key emphasis here is I'm not assuming X is random at all. That's just like in Alberto's paper. Our X here is fixed. I'm not even assuming R is random. Okay, R may or may not be random. I don't know, because if it's like all the non-response, somebody may just always non-respond. They never want to respond to you. So you may ask, like, how would you do any statistic if nothing's random here, right? There's no R, no X, no random. Well, don't forget we have a population here. So here is the little trick. Okay, I'm talking about trick. Mention the trick. Well, anytime you have a sample average, whatever average you take, you can think about you have a probability, uniform probability distribution with n elements, because taking average is the expectation with respect to that index, right? Because everyone get the 1 over capital N, whatever you're doing, right? So that's trivial. Okay, once I do that, I can write this thing. So this will be just the expectation of this G, whatever. So the random variable here is the index, okay? And this is the what? This is the expectation of the product divided by expectation of the R itself. If I take a common denominator, the numerator is the expectation of the product minus the product of expectation. What's that? Covariance. Once you have a covariance, I can standardize by divided by standard deviations, right? One of the standard deviations, remember R is 0, 1. So it has the P minus P binomial ones. So that will give me this factor. The other one, I need to balance, okay? So all I did here is I made no assumption in the simple algebra. But I'm going to now claim that these 3 quantities tell us what's going on here. And you can see this is very applicable because all I have done is algebra. I'm not talking about any specific content. So therefore, it can be applied to very generic. Is this part clear? There is one hidden assumption. Yes.
Wasn't clear to me. I apologize.
Yeah.
Why is so the index 1 through n is fixed, right? X1 through xn is fixed. So
yeah.
Why is i's index random? I mean, are you picking a subsample of them or something?
No, you don't have to, because every time you write, if you write the expectation with respect to probability, right? You'll be averaging over, what is the mass? What is the point mass for each observation? Yeah. But each observation I'm giving the probability is 1 over capital N. It's just a mathematical trick to write average as the expectation with respecting that. You don't have to use this. You can just do the average calculation, but this is much clearer to see where all this correlation comes in, okay? So what does this correlation mean? That correlation means that in the population, every one of you has an X value, has an R value, so in the whole population, there's a correlation, right? So I'm truly doing a finite population calculation. Okay, is that clear?
Yeah.
Okay. All right. So now why do yes?
I could have not put 1 over n's, right?
I'm sorry?
I could have had different weights.
You could have what?
So
Yes.
here you weigh everything equally, and like one can also critique like why,
Yeah. Later there is a formula to be to be the weighted version.
Okay.
But here all I've done is not a model sum. It's not like I assign a weight. I'm re-express this difference in terms of this.
Yeah.
Right? It's a simple just re-expressing.
No,
So there's a subtle point here that basically says all you need to know distribution is uniform. Because everything else is just really aggregates, things that declare them to be the same. Right? So this is just simply a device trying to see what is the key thing in this difference. This is okay. So you write this quantity. Now you may ask, why do I make life more complicated to take one difference into these three? What I'm claiming is these three quantity tells us the problem with all the statistical estimation problem can be written. There are three factors to affect your estimation quality, and there's only three. Okay. Now, based on the condition, I already taken the method is taking average. More general, there's another component is what method do you use? Here is the method already given. This is the simple case, okay? So now, the first component, that correlation is what I call data quality. Because that one measures, right? That measures the correlation between whether you get in or not and the answer you will be given. So if that two things correlated, you will have problems because that's a selection bias come in, right? Or it's basically you are in and out. If it's truly representative, whether in or out, if it's a random, shouldn't depend on whatever your value is. And that correlation directly measures your bias here, okay? So that's the data quality one. It's a correlation, so it's kind of scaled away on a scale. The second one is data quantity, right? The second one is simply said, it's how many samples are not get selected, right? And how many are in. And that ratio, you can see why that's control the quantity, okay? And that tells you, well, I'm going to say in a minute why the quantity is not the key. The last part has nothing to do with your sampling. It's simply the population variance of the G. That is what I call the problem difficulty because that measures the heteroscedasticity among the population, right? So, the simple example is that everybody has the same value, you just only need the sample size 1. You will get everything right. But this is a multiplicative decomposition because this guy is a 0 if any of them equal to 0, right? If everything is homogeneous, as long as n equal to 1, this is 0. If you have everybody in the population and assuming there's no measurement error, so that's one assumption of this formula, no measurement error, you'll be 0. The other thing it says, if you can make that correlation 0, you'll be done, okay? So that's where the probabilistic insights come in. So what does probability do? Probability sampling is trying to make this guy on average equal to 0 or as small as possible. So this gives me a way to measure all kinds of problems because this guy the R coded all kinds of problems in them, whether it's product of 10 or or 20, right? So as I said, nothing is super random, only using the divine probability by n, which is really a mathematical trick. But on the other hand, it's not, because they tell you anytime you have a finite population, you have a natural probability given. You can do all those things. But I do have one assumption, that the sample X in your population, in the sample must be in the population. You cannot have things like oversamples from some other population. Right? So there's a hidden assumption. Everything you sampled is in the population you want. Right? Because sometimes that's not the case. So you have to be careful. Okay. Now I want to make a comparison to the classic bias variance trade-off decomposition, right? Classical bias variance trade-off decomposition, essentially doing a square, you have expectations, and these two terms are orthogonal. But I write in the original version just to be comparable, because there's also square version here, obviously. I write this version because I want you to see that when you talk about a classical bias variance trade-off, you actually inevitably need some randomness to define that expectation. For example, using the R itself is sampling mechanism or some other mechanism. So basically what I'm saying is that the classical variance bias trade-off of forming decomposition tells you there's a problem. You have variance, you have sampling variance, you have a bias. Okay, in general. So it's much more like a phenotype decomposition. It doesn't tell you the reasons. And this decomposition tells you what are the reasons you can get. The problem is too hard, you don't have enough sample, or you have a bias selection correlation there. Okay, so that decompose these things. Now, how do we connect this with the classical thing? And then this is basically what I'm proposing here is we should forget using n or anything else as the index. We should look at this correlation because this correlation is going to be, you will see this correlation is incredibly small when you have random samples. So the formula I have, you can rewrite it, and it just happens that if you divide it by this pretended simple random sample, you do this decompose. This is just rewrite that formula, okay? And if you do the square of them, which I call the design index, the expectation square of them, that turned out to be is just a classical design effect. It's like the design effect is the mean square error or the variance. In this case, because they're biased, I do this by the mean square error. And if you do that thing now, here are the results, and it's very simple to prove. If you have simple random sample, like in Alberto's case, if you have simple random sample, this correlation itself essentially on the order of 1 over square root of capital N. Capital N here, the notation is a little bit in clash. My capital N is the population size. Okay? So basically, this is saying that if you have a random sample, that correlation practically is 0. Our average is 0, but its variance is also 1 over n minus 1. And you can also show that for any probabilistic sampling, that correlation had to be on the order of 1 over square root of capital N, right? And you're also going to show the mean square error, like we always love them. Whatever the mean square error, if it's 1 over n, which is make the probability sampling calculation matters, if and only if this correlation had to be controlled at 1 over square root of capital N. Anything violates that, you no longer have the kind of that's where the bias starts to kill you. Okay. So the deep trouble here is that when we do random sampling or do these things that we control this correlation, we control them at the level 1 over square root of capital N. Once you let people to self-respond or do all kind of stuff, they are not thinking about the population size. That rho essentially is going to be not even depends on the capital N. Once you have a fixed N, this result basically tells you that your error, relative error, is going to be larger. The larger the population, the more errors you have. So this is kind of counterintuitive. So let me just say very quickly that why we typically in statistics, we typically ignore the capital N. That's because we made assumption everything is randomized, right? When it says everything randomized, it's very much like a tasting soup, right? As you mix well, the size of the content does not matter because you already mixed it well, right? But that's a huge assumption. So the whole point is the statistical randomization assumption is when you mix well, of course, the capital N by definition gets assumed away. What I want to show is what happens when we don't mix well. Now here is an example which should be alarming. So you can actually look and say, suppose I have a data set which doesn't have this kind of defect. Let's say this thing is not on the 1 over capital N rate, so that doesn't cancel. That you can write down what is the effective sample size. Basically saying if you have a data set with this kind of defect, what would be the equivalent simple random sample to deliver the same statistical error? Okay, so you can map that. You can write down what this formula is. Now here's the scary part. So let's look at this example given by Walter Dempsey.
Oh yeah.
Suppose New York State, which has about 20 million people, and you did a sample, you did a COVID test, like you did a 10,000 COVID test. Okay. Now we know that at least at the beginning, people get tested not because you don't random test people. You test people when they start showing symptoms or have some kind of contact with people may have that. So there's a little bit correlation there. Okay. Now suppose that correlation is 0.5% correlation. It's not even 5%. Suppose that is a 0.5% correlation, which is way too small compared to what happens in reality. Just with that 0.5% correlation, you can do the calculation, putting this formula. You know that your 10,000 sample size is equivalent to 20, right? I mean, so that is the scale. That's the reduction. That tells you basically what does it really mean? That means that if you're doing the usual calculation, you missed the sigma. You have put about 6 sigma, right? This is actually mixed a square root of 500, means that you missed it by 22 sigma. Okay, and now this itself is kind of a made up example, but now because of this paper, other people having publishing those, and we are publishing in Nature, showing like that the Facebook had this 250,000 vaccination survey, end of the sample size when we do this is about 10. Okay, so the reduction is huge just because, and it's not surprising because at the end of the day, when I have a very large sample, it's not the sampling variability matters. It's 1 over the n. It's the bias. The bias stays. To compensate the bias using the sample size, it's a losing game. Okay. So let me. So this is basically saying that little point of 5% of correlation is already get you 99.8. A defect. And where this 0.5 correlation come from? This was actually I did a study for the 2016 election. Right. In the election, we know the truth in the end. So we back calculated what that correlation is for every state. Like people decided when they report a vote for Trump or not, and you can see very clearly because there's a 51 kind of a correlation. When they ask people whether they vote for Clinton or not, that correlation centered around the right because this is at the level of a 1 over square root of the capital N. But when you ask for Trump, you have this shift. You have shifted by just kind of 0.5%, but that 0.5% destroys the whole thing. You get a very you get a very wrong answer. So here is a weighted version. I always like the wait, don't tell me because the weights are. This is from Duck River. Weights are tremendous, and so you can do all these calculations, and these calculations will show you that kind of Kish's corrections, so on and so forth. I'm not going to talk about that because we're running out of time. So let me just do one more. I should have stopped, but let's do one thing that very quickly. What this thing tells, give us an insight. Remember, you guys might have heard about these doubly robust estimator, propensity scores, all sorts of things. This gives a unified way of thinking about why double robust actually works. Like imagine you have two samples. One is non-probability sample. The other you have an auxiliary sample. So typically, what people do, right? You will have these quasi-randomization. People will say, well, I'm just going to reweight doing propensity score estimation, then just weight that sample by itself. Right? And then you have these modeling people, they would say, well, let me try to model Y and MX, right? Then because the ancillary sample itself is assumed to be representative. So I can estimate the MX quite nicely. Now I'm going to apply this quasi-randomization only to the residual, right? So you get these two. And then there are people like, Jamie Robbins would say, well, actually you can have these estimations will be doubly robust. No matter which way, you'll be getting right. It turned out that it's very easy to see this in this framework because all you have to say, remember we have this covariance matrix, that covariance structure. If you write down this estimate, you will see this estimate, the error is essentially controlled by this covariance. The first part is the pi. Pi is the probability, the probability it gets selected or not, and this is the weight. The second part is the residual errors. So you can see all these different methods, they're all trying to drive this covariance to be zero. So there are two ways to correct covariance to zeros, right? One is, covariance of the two variables, if one of them is constant, that covariance is zero. So if you make this thing to be constant, you got the quasi-randomization answer. If you make the residual modeling errors to be uncorrelated or to be zero or as a constant, you get all the superpopulation ones. But once you see this, you say, now I understand that where double robustness comes from. I don't need to know which one. As long as one of them is constant, it's double robust, right? So more importantly, you realize that you can have both propensity score wrong and your model wrong, but as long as this correlation is zero, you can still get it wrong. You can still get it right. That's what I call double plus robustness, right? And it actually turned out to be, this is what is something, it's actually knowing the literature, Jamie told me. I mean, there's a simple example to illustrate, but this is what, Mark Vandella has been working on, called this collaborative double robustness. that everything is about that correlation. So all we are doing is all we're driving it down is that correlation. Make a variable constant of one or the other, or one of them, or the ultimately you can show that these estimates are consistent. This is not even a method. This is like a criteria, because all I did is to rewrite the bias, direct error, as this covariance. So you see that whatever works, the covariance had to be 0. It's a simple algebra, but this gives a unified way of thinking about these problems. So all we have to do is, like, no matter how many layers problem is, you want to make sure that whatever the final R coming is uncorrelated, as much as uncorrelated with a variable of interest. How do you do that itself? Of course, there's all kinds of trick, but I hope this provides a more unified way of thinking about these problems, not get lost because there are way too many R's there. Okay, thank you very much.
Thank you.